Welcome to Science with Robert, a YouTube channel dedicated to sharing science with you in a fun and interactive way. Enjoy!
Join Dr. Smith and I as we show you how to do some very strange and attractive magnetic experiments. The force of magnetism flows from one pole of a magnet to the other pole of the magnet. Together, all the magnetic, attractive, and repulsive forces that surround a magnet are referred to as the magnet's magnetic field. You can actually see the magnetic field in real time surrounding any magnet if you view the magnet through a piece of magnetic field viewing film. Magnetic field viewing film contains small flakes of nickel that are floating in microscopic oil droplets, and in the presence of a magnetic field, the flakes flatten themselves and reflect light, allowing us to see the magnetic field of the magnet. This is a cylindrical shaped neodymium magnet. Let's see if we can use the film to determine where the poles are. If we stand it on either end, we see a dark circle surrounded by a bright light. Such ends are the poles of a cylindrical magnet. If we lay the cylindrical magnet on its side, we can see where the magnetic forces are located overall on this magnet. The magnetic forces are concentrated on the ends and the center of the magnet. Notice when the film is held above one of the magnet's poles, the light is spread out and diffuse, indicating the magnetic forces are also spread out and weak. And when the film is lowered and set on a pole, the light becomes stronger and more concentrated, indicating that the magnetic fields are strongest in these locations. Dr. Smith has a magnetic ball bearing and a non-magnetic regular steel ball bearing. Which is which? Using the magnetic field viewing film, it is clear the bearing on the left is the magnetic bearing. A spherical magnet doesn't have any ends, so how do you find the poles of a spherical magnet? Dr. Smith is rolling the magnetic ball around and trying to find the poles with the film. The solution is to place a second spherical magnet a close distance, and the magnets will orient themselves aligning their opposite poles. Now with magnetic field viewing film, we can see the poles of the spherical magnet. Okay, Dr. Smith, stop playing around. And let's move on and look at refrigerator magnets with the viewing film. It is interesting to look at different refrigerator magnets with this film. Here are several magnets from Dr. Smith's refrigerator. Dr. Smith is going to use the cubic neodymium magnet as an eraser to clear the film of any previous image so each magnet's field can be more easily seen. First, this is what the cubic neodymium magnet looks like under the magnetic field viewing film. When the magnet is laid on this side, we can see its poles. It is straightforward to see the magnetic field lines of refrigerator magnets. Flat refrigerator magnets are actually mini magnets, separated by only a few millimeters, constructed all on one side, the side that is in contact with the refrigerator. These millimeter-separated magnets have alternating north and south poles. You can actually feel alternating attraction and repulsion if you slowly rub two similar or identical refrigerator magnets together. Refrigerator magnets are made this way because it not only creates twice the holding power on the steel refrigerator, it also creates a uniform magnetic surface with the same attractive power over the entire flat surface of the magnet. Notice on this heart-shaped magnet, we can see an area where there's a defect in the refrigerator magnet. How could that defect have been made?
Maybe it was cut.
Okay, Dr. Smith will try to create a defect in the magnetic field of the magnet by placing a deep scratch in the refrigerator magnet surface. Let's see if that demagnetized the magnet. Nope, can't even see the cut in the viewing film.
I mean cut in half. How about that?
Okay, let's try cutting a section of the refrigerator magnet off. Will that demagnetize anything? Nope, the refrigerator magnet still has its magnetic field, as we can see on the magnetic field viewing film, or just by seeing its attractive magnetic force to steel. Strong magnets were used in the manufacture of refrigerator magnets. So can strong magnets also destroy a refrigerator magnet?
Now that's a good idea.
Let's try it. Dr. Smith is placing a neodymium magnet directly on the refrigerator magnet. Let's use the viewing film to see if anything happened to the refrigerator magnet.
It worked!
The area directly under the neodymium magnet is no longer magnetized. But is the refrigerator magnet really demagnetized? Watch this time as Dr. Smith rubs a neodymium magnet over the entire surface of the refrigerator magnet. Yep, it really becomes permanently demagnetized. Now Dr. Smith is just playing around. He is going to write my name by demagnetizing the letters of my name on a refrigerator magnet. I guess it kind of worked. Looks better than my paw writing, that is for sure. Magnets only stick to metals that contain iron, nickel, or cobalt. A magnet does not attract paper, so why is it attracted to this dollar bill? The U.S. Treasury places iron in the ink used to print U.S. currency. It is the iron in the ink that the magnet is attracted to, not the paper. Magnetism and electricity are very closely related. For example, a moving magnetic field close to a wire coil creates a current. Current is just moving electrical charges, like electrons moving through a wire. Current creates magnetic fields. And when a wire with current is placed in a magnetic field, a magnetic force is exerted on the electric charges in the wire. Let's do some demonstrations of each of these interrelated properties of magnetism and electricity. Dr. Smith is going to illustrate how a moving magnetic field can generate current in a wire. Dr. Smith has an ammeter, which measures current, a coil of wire, and a magnet. He first connects the ends of the coil to the ammeter. When he places the magnet close to the coil and does not move the magnet, no current is generated, as read on the ammeter. However, when he moves the magnet, current can be measured. Notice the faster he moves the magnet, the more current is generated. Do you also see that the current read on the ammeter alternates from being positive and negative depending on which way Dr. Smith is moving the magnet? He is actually generating alternating current as the current is changing direction with the direction of movement of the magnet. This is how a dam generates electricity. A dam generates electricity by using the water traveling through the dam to spin magnets that are surrounded by coils of copper. Dr. Smith is dropping a steel bearing down a copper tube. It fell quickly, just like expected. But watch what happens when he drops a magnetic bearing down the same tube. The magnetic bearing falls a lot slower. We can see why the magnetic bearing falls slower if we use the magnetic field viewing film. Watch the film as the magnetic bearing falls through the tube. Did you see the magnetic field? Cool, huh? Whenever a magnet falls down a copper tube, it generates an opposing magnetic force in the copper tube that slows the magnet as it falls through the tube. Magnets fall very strangely down aluminum and copper tubes. I think this one is really cool. Dr. Smith is going to illustrate how magnetic fields exert a twisting force on moving electrical charges by constructing a homopolar motor. Recall that moving electrical charge is also known as a current. As the diagram illustrates, Dr. Smith will create his homopolar motor by passing a current through a wire that runs very near the strongest part of the magnetic field of a magnet. The magnet will be magnetically attached to an iron nail, which magnetically attaches to the positive end of the battery. The nail allows the magnet to spin freely with very little friction. Dr. Smith is first attaching the nail to the magnet. He is now making electrical contact with one end of the wire and the negative end of the battery. Now when Dr. Smith touches the other end of the wire to any part of the nail or magnet, he will be making a complete circuit, and current will be flowing through the wire. When he makes electrical contact far from the magnet, the current traveling through the wire feels very little magnetic field strength, and thus little, if any, twisting force is created. As electrical contact is made closer to the magnet, the strength of the magnetic field increases, and so does the generated twisting force.
Hey, it's starting to spin.
From the magnetic field viewing film, we know the magnetic field is strongest near the poles and the center of the magnet. So if electrical contact is made there, we achieve maximum torque generated from the magnetic field and electric current in the wire. Notice that even though it is the charges in the wire that the torque is applied to, the wire is fixed in position. So it isn't the wire that moves, but the loosely hung magnet.
Hey, that sounds like Newton's third law.
Yep, and you can generate some pretty high speeds with this type of homopolar motor, so be careful. Magnetic fields can be seen with ferrofluids. Dr. Smith made some ferromagnetic solution. Here are the ingredients he used. The ferromagnetic material was extremely fine magnetite. The carrier solution, kerosene. And to keep the magnetite fluidic, he is adding a surfactant, oleic acid. The surfactant completely surrounds the magnetite and isolates its attractive forces from its chemical neighbors. He adds roughly 5% by volume magnetite to a mixing container, followed by roughly 10% by volume surfactant, and mixes well. He's now adding roughly 85% the remaining volume of the carrier solution. The weird properties of ferrofluids can be readily seen when added to water, which is what Dr. Smith is doing now. As you can see, a magnet readily attracts the ferrofluid. When held just right, spikes can be made in the ferrofluid. The spikes are in line with the lines of the magnetic field of the magnet. Let's review. A moving magnetic field close to a wire creates current. This is how dams generate electricity. Current creates magnetic fields. Magnetic fields exert forces on moving electric charges. Magnetic field viewing film is used to see the strength of magnetic fields on magnets. Falling or rolling magnets will magnetize the metal they are traveling on or through and slow themselves down by generating a magnetic field in the metal, which opposes the magnet's magnetic field.